So we're going to look at something that's completely brand new in this unit. Probably the first thing that's completely brand new in this unit, and that's working with radicals. So you've all gotten radicals or square or roots in your answers at some point throughout the year and previous years, and what we're going to look at now is how we can work with them and sort of simplify them a little bit more. So what I'm going to do first before we get too far into it is I have 10 different expressions involving roots or radicals down here, and I want you to use a calculator just to evaluate them. So once they're evaluated, I want you to group them together, and once you see them in groups, I want you to try and figure out any patterns that you might see that might sort of let us come up with some rules that we might have for simplifying square roots. So again, evaluate all of these 10 using a calculator and split them up into groups, and then see what kind of patterns you might see. So once you've grouped them, you'll see that 4 of the 10 of them were equal to 3.873 approximately. The other ones were all equal to 7.348. And from here you might start seeing some patterns. So you may notice here that root 15 is equal to root 5 times root 3. You might be able to try and figure out a rule from there, because really what is 5 times 3? It's 15. Root 75 divided by root 5, well, what's 75 divided by 5? Also 15. And you might see something going on here with these roots as well that we're adding subtracting. We have 6 root 15 minus 9 root 15 plus 4 root 15, which is all equal to just 1 root 15. And maybe try and think about where that comes from as well. You might see some other rules too. Over here, root 54 is equal to 3 times root 6. We're trying to think about where that came from. Here we have 5 root 6 minus 2 root 6, which is 3 root 6. Maybe you see something to do with like terms that might come into play. So take a look here and just see what kind of rules you might be able to try and generalize. And let's summarize them over here. So first thing you might see is that we have the product rule, which means if you take two square roots and multiply them together, what's under the root multiplies together to give you one gigantic root. So you might see that in an example over here when you have root 5 times root 3 gives you root 15. 5 times 3 is 15. Okay, so that's the product rule right there. Similarly, we have a quotient rule, which tells us that if we're doing division of two square roots, we can combine that division under one giant root. We can add and subtract like radicands. Now, think of it, back in grade 9 when you were collecting like terms, right? If you had 2x squared and x and 3x, you could only add the x terms together. That x squared wouldn't be mixed in. Kind of similar right here. If you have, let's say, 3 root 2 plus 5 root 3 minus 6 root 2 plus, I don't know, let's say 12 root 2. You can do some simplification here, but only with the radicands that are like each other. So we've got root 2, and root 2. We can add the coefficients here. 3 minus 6 is negative 3, plus 12 is 9. So those three together, again, if I'm combining this one, and this one, would give me 9 root 2. There'd be nothing I could do with this 5 root 3 because there's no other root 3s to combine it with. So I'd get 9 root 2 plus 5 root 3, and this would be a more simplified form of that kind of expression. Similarly, we can also do what we call mixed radicals, which are in lowest terms. So this, for example, right here, 3 root 2 is a mixed radical, has a coefficient in front and something underneath the square root. Or we can have something called an entire radical where there's no coefficient out in front. We'll look at some examples of that coming up. Another thing to remember here is if you're looking at the root of a times the root of a, that's going to be equal to a. So a good example here would just come from looking at, you can try it in your calculator. If you have root 3 times root 3, well, that's just going to be equal to 3. Okay, similarly, if you think about it, you can have root 4 times root 4, and since square root of 4 is a nice perfect number, it's just 2 times 2, and that whole thing is equal to 4. Okay, so this relationship is true for any value of a. Alright, so I'd mentioned going from entire radicals to what we call mixed radicals. Well, when we want a mixed radical in those terms, that means we want what's underneath the square root to be as small as possible. So this is what we call an entire radical. It's just one giant number underneath the square root. So to put this in lowest terms, what we're going to be looking at here is we're going to try and find the largest perfect square that is a factor of 48. The largest perfect square is a factor of 48. So when I say perfect squares, I mean like 1. Because 1 squared equals 1. If you do 2 squared, you get 4. So 4 is a perfect square. 3 squared gives me 9. 9 is a perfect square. So I can keep going, right? 16 is a perfect square, 25 is a perfect square, and so on and so forth. I keep going on forever. So what we're looking for here is the largest perfect square That's a factor of 48. So if you're looking at this, well, okay, the one that jumps out at me is 16. So I can rewrite this as the square root of 16 times 3. Because again, 16 times 3 is 48. I'm just rewriting the 48 in a different way. And now, using my multiplication rule, I know this is the exact same thing as the square root of 16 times the square root of 3. Okay, just splitting up to two different square roots. And since 16 is a perfect square, the square root of 16 is a nice whole number, it's equal to 4. So the square root of 16 is 4, and I wind up with 4 root 3. Okay, so right now we put it in lowest terms. The value that I have here, the 3, is not, there's no perfect squares that go into it. In fact, it's actually a prime number, so I'm finished. Okay, and I can do something very, very similar over here. If I look at 72, the largest perfect square that we can factor out of that is 36. So I'm going to keep my 5 out in front here, and then inside I'm going to have the square root of 36 times 2. Okay, dot for multiplication there. So this will be 5 times the square root of 36 times the square root of 2. Square root of 36 is equal to 6. Once you get really good at these, you may be able to skip some of these steps and just going through where all those numbers come from. And then 5 times 6 gives me 30. So this whole thing simplifies to 30 root 2. And again, now I've put that into lowest terms. So going backwards, I want to put things as under an entire radical. Well, now I want everything under the square root. I don't want any coefficients out in front. So now I'm going to picture, okay, if I could express 5 as a square root, what would it be? I.e. the square root of what is going to be equal to 5? Well, if I go backwards, if I square 5, it's 25, so I can rewrite 5 as the square root of 25. So I have the square root of 25 times the square root of 3, which I can combine to get the square root of 75. Okay, now for this last one, I'm going to do something similar. One little trick, though, here comes with this negative. I'm going to leave this negative alone, and I'm going to show you why after. So I'm just going to take the 4, and again, the square root of what is 4? Well, the square root of 16 is 4. So I'm going to rewrite 4 as the square root of 16. So the square root of 16 times the square root of 6. So I can multiply those square roots together using multiplication. And that's going to give me the square root of 96. Okay, and I'm going to leave the negative out there. The reason I'm not going to involve the negative in here is because there's nothing that I can take the square root of to give me a negative 4. So if I try and incorporate this negative in here and say, okay, well, negative 4 all squared is positive 16, then I could wind up with something along the lines of root 16 times root 6, which again would give me root 96. But there is no possible way out of here because I can't take the square root of something and get a negative number that would wind up with this original value. So if I try and incorporate this negative into the square root that I'm trying to create here, I'm going to get something that's incorrect. So when I have a negative out in front here, even though I want this as an entire radical, I cannot put that negative inside the square root. There's nothing I can do about that. So if you see that negative in front, just leave it out in front and leave it as part of your final answer. Otherwise, you're going to be creating something that's not equivalent. Okay, so let's keep going. Let's try a few others here. So a lot of this is just getting used to some brand new rules. So here I'm trying to simplify something, I put it in lowest terms. This is adding and subtracting here. And one of the rules that you might remember from a couple slides ago is we can only add and subtract what we call like radicands. So they have to have the same value underneath the square root. So if looking back at this one, the only ones I can combine together are my root 6's here, and then separately I can combine my root 7's together. So I'm going to put my coefficients together here. I have 4 root 6 plus 9 root 6, which is going to give me 13 root 6. And I have negative 3 root 7 plus root 7, which will give me minus 2 root 7. Pardon me there. Minus 2 root 7. Okay, as a rule, we want to express everything in lowest terms from now on, unless I say otherwise. So both root 6 and root 7 are in lowest terms. There's no perfect squares in there. So this is as simplified as we can get this one. We're actually done here. So if you look at part B, at first glance, there actually is nothing we can do because every value in the square root is different from each other. You've got root 75, root 2, root 18, root 3. None of them are quote-unquote like. It's not the same value into the square root, so we can't combine anything. However, if you take a second look, we can actually simplify some of these. So root 75, if you picture a perfect square that comes out of root 75, well, 25 goes into 75, so it's the same thing as root 25 times root 3, because 25 times 3 gives you 75. So I'm going to get minus 8 root 2. 2 doesn't break down any further. 18 has a perfect square of 9 inside of it, so I'm going to get plus 4. Root 9, and 9 times 2 gives me 18, so root 9 root 2, and again my plus 6 root 3. So I can actually simplify this down a little bit further to eventually get like radicands to simplify with. So take this further. Square root of 25 is 5, so I get 5 root 3 minus 8 root 2. Square root of 9 is 3, so 3 times 4 is 12. I get 12 root 2 plus 6 root 3. And now you can see there's actually some things I can combine here. 5 root 3 plus 6 root 3 gives me 11 root 3. And negative 8 root 2 plus 12 root 2 gives me 4 root 2. So now this is simplified as far as I can go. So always look at the radicals you get and see that they're in lowest terms before you start walking away from a problem and decide that you can't simplify it any further. Because again, when in doubt, simplify as much as you possibly can, and it'll make your life a lot easier. Okay, let's keep going. So now we're going to look at the multiplication. So we've got square root of 5 times square root of 7. Using our product rule from one of the opening slides, this is going to be the square root of 5 times 7, which is going to be the square root of 35. And for the one over here, we have got coefficients to multiply and roots to multiply. So I'm going to do it piece by piece. Start with the coefficients. So I'm going to have 7 times negative 4, which will give me negative 28. And I have root 6 times root 21, which will give me the square root of whatever 21 times 6 is, which should give me 126. Okay, and again, with both of these, before we can say we're done, we want to check to make sure they actually are in lowest term. So I didn't actually do it with this first one over here. If I look at the square root of 35, are there any perfect squares that go into 35? The answer is no. So 1, 4, 9, 16, all those, none of them go into 35. However, with 126, if you take a look and go through them, we can actually take 9 out. So when you get negative 28, I can rewrite 126 as 9 times 14. And again, I'm looking for that perfect square that is a factor of 126. So I can simplify that into negative 28 times root 9 times root 14. And again, you might be able to skip this step and go right to the next one if you need to, but you get negative 28 times 3 times root 14. And negative 28 times 3 gives me negative 84. Okay, so again, always check to make sure your answers are expressed in lowest terms. Okay, so I'm going to continue these next few examples in part 2 of the video. So I want you to try these on your own first. This is division that's going on here, so try your rules, try and simplify it, put it into lowest terms. We'll continue this in the last slide of examples in the next lesson. Okay, we'll see you there.